Welcome everyone to the first seminar in the AIP Theoretical Physics Seminar Series for 2022. I'm David Tilbrook at the Department of Fundamental and Theoretical Physics at ANU. And I'd like to start, as always, by acknowledging the people of the Ngunnawal Nation on whose traditional lands we now stand at ANU, and also recognise the custodians of the lands all around Australia. We give our respects and acknowledgements to their leaders, past, present and emerging. Last year's talks are all available, as this one will be, on the AIP YouTube channel. So we invite you there to go and have a look at those if you need to catch up. Today's speaker is Professor Magdalena Zych, I think I got that right, from the University of Queensland, who is going to talk to us about composite quantum particles in the interface of gravity. It's a really fascinating emerging field, in my opinion. Decades ago, I did my PhD in quantum field theory and curved space-time, so it's of particular interest to me. I've been looking forward to it. Dr. Zych is the recipient of the 2020 AIP Ruby Payne Scott Award for the development of some of this work. I think without any further ado, I'll just say over to you, please, Magda.
Thank you very much for this introduction, and I'm also glad to see some people are able to join, and we are all aware that many will be impacted by rain or flood or still the coronavirus. So it seems, or cut cables if you are in Tasmania. It seems, yeah, it's still challenging time. So all the more I really appreciate colleagues at the AIP that managed to get this seminar running again in the new season, and I'm really happy to give the first seminar. And so yeah, maybe without further ado, I'll share my screen, and we can get started. I guess in case David, you'll let me know if there's anything wrong with the screen. Otherwise, I assume we can get going.
No, it's perfect, Magda.
Awesome. Yes, I'll be talking about some fundamental aspects and interesting insights that one can gain by studying composite quantum particles in the context of general relativity. And indeed, some of this work was recognized by AIP with the Ruby Payne Scott Award. So I'll mention this in the first part of my talk, and then I'll talk about some more recent insights that I think will be interesting for the broad spectrum of people that I assume are joining here. All right. Since there is often very little time left at the end, I wanted to start with mentioning the obvious fact that this work is not done in isolation, that myself and my students, we collaborate with many groups all over the world, and the results are often obtained in collaboration with colleagues spread across a few continents. So since I will be talking about quantum and gravity research, I would like to start with highlighting various possible aspects of that research and then clarifying what actually my research looks at. So you might be familiar with using quantum physics to think of improving the precision of some tests of general relativity. I would assume many of you would have heard about the idea of using squeezed states of light in the LIGO and other gravitational wave interferometers that may allow us to effectively reduce the noise. Another aspect that obviously one would hear about being a physicist is the research on quantum gravity. So this is exploring mathematical frameworks of string theory or loop quantum gravity or causal sets and other other frameworks. So what my research is about is looking at the interplay between quantum mechanics and classical general relativity. So as actually David mentioned, quantum mechanics in curved space-time, and asking the question, what are new effects there, new in a sense that do not appear in quantum mechanics in the presence of non-relativistic gravity, so some Newtonian non-relativistic Newtonian effects. So what are the effects that can disprove the description of non-relativistic gravity, and also how minute general relativistic effects can actually impact very high precision quantum technologies that independently people are striving to develop, or some quantum information exchange protocols over large distances and maybe across gravitational fields. There's also an active research in what one often calls alternative gravity models, or alternative ideas about quantum mechanics and gravity, where one asks the question, what can we say about whether gravity can actually, whether gravity actually needs to be quantized, or maybe there is some new physics that arises when quantum source masses are present, or source masses of gravitational field are put in quantum states. I'm also involved in such research, but today I will focus on just this top corner. And so the reason to look at tests of quantum mechanics and beyond Newtonian or general relativistic gravity effects is that even though we are all exposed to this idea of the holy grail of theoretical physics being quantum gravity, when we ask what have we tested about quantum mechanics and gravity together, it turns out that all experiments in which we have the same degrees of freedom that require both quantum and some aspects of gravity to be described, all these experiments can be fully explained in terms of a non-relativistic Schrödinger equation where gravitational potential enters as any other potential, like maybe electric potential. So here you have an example of energy of a particle with some mass parameter m, and it's in the gravitational potential that is additionally written in a homogeneous gravitational field limit. And so if one prepares a particle that is in superposition of different heights h, then recalling your kindergarten quantum mechanics, you will realize that there will be, because of the evolution with the Hamiltonian, there will be a different phase that is acquired by states localized at different heights. And such a relative phase can be measured, for example, in the interferometer. So the photo you see in the top right corner is a photo of one such interferometer, a relevant one because it was used in the first experiment that has detected this kind of relative phase through interferometry. So this is the first reference in red, referred to as Cow experiment from the surnames of the author. So this has been a neutron interferometry experiment. So neutrons were going through these three crystal slabs where first and last essentially serves as a beam splitter, and the middle one sort of to recombine the beams of the neutrons. So this was 75. And since then, similar experiments were done both with neutrons and other systems. The most precise of such experiments are now done with atoms. And instead of such a physical crystal to implement the interferometric scheme, one uses standing waves of light in the position of these gratings to diffract the atomic beams, essentially. And so something that I would like to highlight in particular is that up till 2017, all experiments of the type that we had were not just only sensitive to the non-relativistic Newtonian potential, they were actually fully described with this homogeneous gravitational potential. And the first experiments where one had to include corrections to this potential that come from the fact that gravity in a typical place on Earth is not homogeneous. The first such experiment is this reference from 2017 from the lab of Mark Kasevich. So it's not just that up till then we haven't tested any quantum gravity effect. Up till then we haven't really tested quantum mechanics beyond gravity, where it's fully analogous to constant acceleration. There is just maybe quickly to mention another physical effect that arises for systems trapped in a potential. And this is quantization of trapped state. So when you have some potential that can bound the system, the eigenstates are like your square well, have some quantization of possible energy levels. So the same happens when you have gravitational potential on one hand, and on the other hand, say some reflective surface that prevents a particle from falling through. So this way you can create this kind of wedge shaped potential where the reflecting surface can be modeled as infinite potential, and then this linear potential that you see in the plot is just the gravity. So solution for this kind of potential are Airy functions. And again, with neutrons, it has been demonstrated that indeed neutrons trapped by gravity above some marble slab have quantized. So this is a photo of the setup again, and the authors of the paper that have demonstrated it for the first time. It has been demonstrated that indeed neutrons have quantized energy levels in such a scenario, as well as the fact that the probability to find a neutron exhibits this kind of quantization. So you here see the Airy functions, and so if you in space, and it tells you that the most probable place to find a neutron is when there is the maximum of the wave. So for the different levels, there would be discrete in space positions where it's most likely to find a neutron, and this has been observed as well. So I think it's just a very elegant idea and very cool experiment. So I would like to, that's why I wanted to mention it, even though it demonstrates the same regime. So non-relativistic particles that are subject to a potential, and everything can be described in some Euclidean space with absolute time, and fully compatible with the non-relativistic description. And so, of course, it's not that we haven't tested other effects because we don't have a theory at the fundamental level. Again, it has been mentioned that we do have quantum field theory in curved space-time. So just a highlight of some key textbooks if you haven't been exposed to the topic. And so what's the issue with directly testing some of the predictions of these theories is that usually the highlights, the new effects that are studied within this framework arise at high energies. So these are theories of elementary particles. You might have heard of Hawking radiation from black holes, or Unruh radiation that is associated with the non-inertial reference frames for fields. Where at high accelerations you might find some analog of the Hawking radiation. And so the issue is that the regime where these effects appear is just very hard to reach by experiments. And so the question that we've been asking in our research is, what can we do about this if we only consider that we have the possibility to make experiments at low energies and a weak gravitational field, so essentially a lab experiment. And the strategy is to include internal degrees of freedom of composite particles. And so that's That's going to be the focus for the rest of the talk. And so I'll start with briefly outlining the key aspects of the framework and highlighting the key result that demonstrates why it is a good idea to look at such composite particles and how relativistic effects can be observed at low energies using this approach. And then I will mostly focus on the bit about what are the semi-classical states for such composite particles, because I think it's perhaps the most generally accessible and of broad interest to hear about this result. And so without much warning, I'll toss at you this Hamiltonian. So this is essentially the energy of a single particle in some static symmetric metric. The G0 for those that are familiar with GR is the time component of a metric. And then I imagine most of you will recognize the p square plus m square term that yeah, you might be familiar with classical relativity. Now we are interested in particular here in the limit of single particles, so where the creation annihilation of the particle itself type effects are negligible. So we consider particles of the type of atoms that we can describe with first quantization. So if you want to see how to derive this particular expression from field theory, you have some references here below, but we will directly just use this dispersion relation. Now, the detail here that you may notice is I've put a lot of heads around. So this just to mark which of these objects are operators associated with some Hilbert space. And there is also a head on the M. So what I mean by this is that we consider systems which in their rest frame have some internal, have some energy. And so this is by definition the rest or the rest frame energy or internal energy, depending on the terminology. And again, a typical such system and really our model for what's going on here is an atom. And if you're in the rest frame of the atom, it will have all its electronic and other levels. So in that sense, these are point particles. So we don't consider effects that come from the actual spatial extent of the atom in space. And that's why point, but with internal structure. So this is the idea that in the typical weakly varying gravitational fields, like in the lab, the extent of the atom itself can be neglected, but not the fact that it has all the internal energy levels. And of course, by treating the position degree of freedom of the atom as well as its internal energy quantum mechanically, we can consider arbitrary spread wave functions or states for the atom. So this point-like nature does not constrain the possibility of looking at some large superposition states in space or momentum for these systems. Now, we want to look at low energies, and I will take an approximation that really looks like we went completely too far. So if you remember how you obtain a Newtonian limit from this kind of relativistic dispersion relation, you just expand things to zeroth order in c square, and you get the rest mass energy mc square, kinetic term, and the potential term. So the phi of x here denotes the gravitational potential. Now, it's important to understand that this mc square is just a way to denote the rest energy of the particle. And so this means that there is all the internal energy spectrum and all the internal different energy levels that M had describes. So if we unpack it explicitly, so we just separate the ground state and we call it a little m, and it will be clear why that's a good idea or why it might be telling. So we can always do this for any operator And in this way, we essentially define this H internal as the internal Hamiltonian, whose ground state is by definition 0, and essentially describes energy levels above the ground state. And the ground state we denote just M with the intuition that the ground state of the rest energy would play a role of a mass parameter. And indeed, that's what happens. So if we now incorporate this into this seemingly non-relativistic looking Hamiltonian, we see that we actually recover now the fully non-relativistic center of mass part, as we've seen with the neutron, with some mass parameter m, kinetic energy, and some potential term. And then we have internal energy that couples to the potential and the kinetic term that, of course, carries the c squared. But the main thing is that this H internal describes a space spanned by internal degrees of freedom. And so these kind of terms essentially describe the coupling between internal and external degrees of freedom of a particle that that arise because of relativity. They are necessarily there. So this is essentially the main technical aspect of the trick of why including internal composition or internal energies for particles is a good idea if you want to look for some relativistic effects at low center of mass energies. Because what just happened is that we are looking in the regime where the center of mass is essentially non-relativistic, but because internal states have their evolution, we can still see some relativistic effects that essentially can be interpreted as time dilation or redshift. So let us look at this now in some more detail. So the term with the gravitational potential essentially describes the redshift of this internal energy. And the second term, if you consider for a moment a fully classical center of mass, P on M would give velocity. So this is the lowest order approximation to a Lorentz factor. By this, I mean the second term in the bracket. So just to nail this intuition, if you consider that internal Hamiltonian describes some two levels with the energy difference now measured in terms of frequency omega, and we go to the homogeneous gravitational field approximation, then this first term will, if you forget about the kinetic term, will just give the familiar looking redshift factor. And if you forget about the gravity term, then this term, depending on momentum, will just give the Lorentz factor as I described. So this tells us essentially what we do broadly know about relativity, that energy will be redshifted due to gravity or Doppler shifted due to relative motion between a system and the observer reference frames. So for atoms whose center of mass is essentially classical, these kind of redshift effects were tested. These are references from Dave Weinlein's group with, I believe, aluminum atoms in optical traps. And there were separate sets of atoms at different benches, positioned at relative heights, and they differed by 17 and 33 centimeters. And you could kind of move the potentials to create a relative motion between these clock ensembles or atomic ensembles, and indeed verify that the frequency of internal transitions or the energy gaps of these atoms were effectively varied depending on these scenarios. So these experiments, indeed, to describe the characteristic frequencies of the atoms in these scenarios, you need to consider quantized internal energies of the atoms. But the position of the atoms essentially were fully compatible with the classical description, even very coarse-grained, as you have seen. It's enough to know roughly the height difference between the independent setups, or roughly the velocity with which the potentials were moved. Now, with the approach we we've been taking, we have an effective Hamiltonian for such an atom, where we describe the center of mass with 1 degree of freedom and internal states with some discretized levels. So we have a full quantum mechanical description of both these relevant degrees of freedom, and we can ask questions now, what happens if the position degree of freedom of atoms in such experiments is quantum mechanical, and what effects can be observed and what scenarios can be considered. So I'll just briefly highlight the main thought experiment that we came up with, and that led to a lot of different iterations, and is subject now to some direct experimental efforts. So the idea is essentially, instead of using a pair of clocks in this kind of experiment, so this kind of experiments with 2 clocks are essentially twin paradox experiments. You have pair of atoms or pair of twins, and you put them at different trajectories through space-time, either at different heights, or one moves with different velocity, like with this moving ensemble of atoms in a potential. And you verify that if initially your twins are identical, or your clocks are synchronized, after all these manipulations, you bring them back together, you compare their dynamics, and you find that it differs precisely because of the time dilation effects. Now, with the quantum mechanical description, we have a chance to answer the question, what happens if we take a single clock or a single quantum twin, and we consider a situation where it moves in superposition of such 2 scenarios. So for example, the atoms are prepared in a superposition of being at 2 different heights in the gravitational potential, and then we bring the different amplitudes back together. So just based on the intuition that we just got, there will be different redshifts and different proper times elapsing for the different amplitudes. So we can already consider an amusing, I hope, for everyone, possibility that there will be a quantum traveler that in the end is both younger and older than themselves. But this framework also allows us to quantitatively answer the question, what happens in the interference experiment where there is such redshift or equivalently time dilation effect between the paths taken by the clock. And so, as we've seen from the Hamiltonian, essentially we have a coupling between internal states and the position, which means that internal states have path-dependent evolution. So that's essentially what time dilation is, or what redshift is. These are the same thing from the point of view of relativity. So very sketchily, what we have is that we start with some superposition state for the path degree of freedom, so gamma, and some internal state. And after some time of evolution, for example, because we keep the clock at these different heights here sketched in the picture, internal states evolve differently. And yeah, one way to interpret is due to this redshift of the internal levels, the energy gap gets scaled depending on the gravitational potential. So lower clock evolves slower than the clock higher above in the gravitational field. And so these 2 different amplitudes will evolve at essentially different rates. So when you recombine the position degrees of freedom in your interferometer, there will be some correlation that are developed with internal states, and they will show up here as a modulation to the interference pattern. So without this term, you would recognize exactly the same type of interference as we've seen with neutrons. But now we have this additional term that describes how well is this cosine, this interference part, visible. And it's therefore called the visibility of the interferometric fringes, or interferometric visibility. If we write the overlap between these states associated with the different paths in terms of the energy, so here this H clock is the same as H internal that I wrote before. And delta tau is essentially the proper time difference between the paths. So the laboratory time scaled with any redshift between the two heights. And so one sees that this term exactly captures the relevance of the proper time. If proper time is 0, this term is always 1. In particular, this means that in a fully non-relativistic limit, this term is always 1, independently of how the paths are set up in space. And so to look a little bit at what are the relevant parameters here and what physical configurations one can look at to see this effect in practice. So time dilation or redshift between two heights separated by some vertical distance h. If you wait for laboratory time t, is given by, again, this familiar redshift. Factor g for us will be the gravitational acceleration on Earth. So this is the redshift or time dilation between the two paths taken by our clock in superposition. Now the other relevant parameter is the internal energy. So again, counting energy in terms of frequency, we find that this overlap is given again by some periodic function if we just consider two energy levels. And this is in fact very intuitive if you think about a two-level system or a periodic a pair of twins. If time dilation between the trajectories taken by the twins is equal to a full period of their evolution, they will be indistinguishable. If it's equal to half the period or multiple, they will be as distinguishable as possible. So if we have superposition of two different energy levels, they become fully indistinguishable every period of evolution, and every half period, after half period, and then periodically, and they become fully indistinguishable after a full period of evolution. So you have, again, a cosine here that just highlights this. I hope, despite my many sleeps, you got the gist. So what we expect in an experiment is as follows. If we have an atom prepared in superposition of internal energy levels, separated by this frequency omega, that is put in superposition of these heights with time dilation delta tau, as we increase t, effectively time dilation, if we were in a fully non-relativistic universe, the only thing that would happen is that because the clock has a mass, it would acquire some phase like we've seen for the neutron, and we would have this dashed line that just tracks the fringe, the phase accumulated. Now, if we are in relativistic universe, or at least a universe where we have a redshift or time dilation effects, there the fact that we are the system evolves at these different heights would mean that the amplitudes or the internal states will periodically become distinguishable and indistinguishable, and we would have this overlay or this modulation to the pure interference that will produce effectively the blue line that you see. So periodically the interference contrast will completely collapse and then revive. So the blue line is a full interference fringe, and the red line is the as this visibility. So just this term that depends on time dilation versus the internal frequency. And so if you want to now consider some particular numbers for when to expect this this kind of collapse and revival of an actual interference, we can consider making an experiment with the internal levels of, for example, strontium atom that are separated by optical frequency. If you are on Earth, then acceleration g is fixed. So just keeping it simply at 10, we arrive at the only remaining relevant parameter, which is the space-time area of the interferometer, essentially this height different h times time t. And to reach this collapse and revival of the fringes, we need of order 10 meter times second of separation. So that's challenging for anyone that knows about matter wave interferometry. These are challenging numbers, but there is a number of efforts to realize this experiment. And maybe I'll just very quickly put up just a little bit of highlight of what's going on in that sphere. So there is a dedicated a building actually that houses a newly built interferometer in Hanover, where one of the science goals of this new experiment is to test this kind of effects. And there are also efforts to test analogous effects that arise for photons. I'll not mention anything about that, but there is a couple of references. So let me move on without further ado. I would like to highlight the fact that I've been frequently talking about redshift and time dilation, while we are here in the Hamiltonian picture, where time dilation belongs or is described in the configuration space. So I would rather call for a Lagrangian. In fact, for relativistic particle, you may recall that the Lagrangian is particularly simple. So it's just for a point particle with mass m, it's just m times the proper time parameterized with any reference frame time t. So this is the general form. So this would suggest that if you want to talk about internal energy levels and how they get time dilated, this actually poses some issue because we would need to sacrifice one or the other for a consistent description. But the point I want to make is that one can consider a different functional that, for example, if you start from Hamiltonian, if you want to obtain the Lagrangian, you do a Lagrange transform of all your degrees of freedom. You can do a partial Lagrange transform and just transform to configuration space the center of mass, degree of freedom, and formally a functional that has this Lagrange transform only for some degrees of freedom, and is therefore some degrees of freedom described in terms of phase space and some in terms of configuration space. Such a functional is called the Routhian or Routhian. And in this context, it's really particularly suitable because we can combine best of both worlds and describe internal and discrete energy levels simply in terms of energy and the position degree of freedom and how proper time changes along the different trajectories of the center of mass. For arbitrary spatial wave function of a system, we can capture this as it's most convenient in terms of the configuration space. And so this is indeed the ideal picture for describing things like ideal quantum clocks in relativity, because we can describe the internal state space of a clock very simply in terms of rest energy and of course the proper time directly as well. But it's also a picture that is convenient for other applications or other contexts in which composite quantum particles can model some idealized kind of sensors. So just to highlight what we can mean by this, you've seen how these redshift time dilation effects essentially appear as soon as we incorporate the fact that in relativity we have mass energy equivalence, so that internal energy weighs, and therefore the rest mass is in fact containing all the internal energies of the system. So these composite particles, I've been highlighting so far what you can test with them if you think of them as traveling clocks or twins, but you can also consider them as quantum test masses, where the quantum is really on, on the mass, in that you consider a system whose mass energy can have different levels. So quantized mass in that sense, something that we are very well familiar from, for example, neutrino phenomenology, where it's clear that the current observations with neutrinos cannot be explained without incorporating the idea that neutrinos of various flavors are superposition states of different rest masses. The same arises effectively for these kind of systems like atoms, where internal energy contributes to inertia, weight, and rest mass energy. Now, for composite particles that are coupled to some external fields, for the simplest such coupling, namely monopole coupling, so a qubit with monopole coupling to external field is known as unruh-Devitt detector, and such effectively composite particle coupled to a field is an idealized particle detector. So we have now a framework to describe quantize both position and internal states of such systems. So we have we can use these composite quantum particles as idealized quantum unruh-Devitt detectors. If you are familiar with research in that context, until recently, these systems were only described in terms of their internal energy levels, and the position degree of freedom was only described classically. So this again allows you to lift that restriction or this idealization. And if you attended the AIP Congress in Brisbane, you might have seen a poster by Evan Gale talking about some results that arise from extending model in that way. And also a system coupled to external environment, if you think of this environment as a thermal bath, constitutes some idealized quantum thermometer. And again, if you had the chance to attend the Congress, you might have seen a talk by Carlin Wood, who was showing some results what happened to thermalization for systems whose internal states thermalize with extended environments where temperature may vary, and where quantum degrees of freedom of the system may mean that they thermalize and well, superposition of temperatures. If you are interested or intrigued what that means, you can try to dig out our Caroline's presentation or our work on that is already on the archive. I'm not going particularly fast with time, so maybe I'll just very quickly put up this slide just to mention that there are a lot of fundamental insights that can be gained from exactly thinking of composite particles as all these idealized type sensors. And I would like to maybe just briefly sketch the idea behind the result that I've been mentioning before, that is the question of what are semi-classically propagating states of composite particles. And so a standard answer, I believe, of any theoretical physicist that is woken up in the middle of the night and ask what is a semi-classical state of some particle with some internal states, we would typically say, well, it's a Gaussian, and then internal states can be anything, especially if one further clarifies we are talking about free particles. So free particle with internal states, we would probably intuitively say, well, it's a Gaussian state for the center of mass. But there is a but to it, and I'll show you where one has to be more careful. So if we start to think a little bit where from these Gaussian states come from, well, essentially they come from asking what are semi-classical distribution or states in phase space, so states that minimize uncertainty principle for position and momentum. So these are states that are as localized in phase space as possible. And in that sense, they are semi-classical. Now we are here talking about particles with internal energy levels, where because of relativity, what this means is that they have quantized mass energy. So different internal states correspond to different mass for the particles. So now if I want to ask the question, what is a semi-classical state of motion of such a particle? And I say, well, something that has approximately well-defined position and momentum, then this is actually not true. So if you think of particle with the well-defined momentum, but has some arbitrarily internal state, for example, superposition of different mass energies, this actually means that it's moving necessarily with some superposition of different velocities. Just if you simply think of the non-relativistic limit of the relation between configuration space, so velocity and momentum. So really, very simply, P is equal M times V, non-relativistically, or in the low energy limit, which means that if you consider a system that has different possible masses, but some semi-classically or approximately well-defined momentum, then it's not going to be moving on a classical space-time trajectory, because essentially it's moving with velocities that are correlated with internal states. So what one needs to do is to ask a different question, and that is, let me maybe put a couple more things, and that is, what are states that have minimum uncertainty for position and velocity? So this will be the states that have semi-classical space-time trajectories. Now, how we should go about describing velocity in this context is very simple. Velocity operator is nothing but time derivative of a position operator. You can see here how it looks for first quantized relativistic particles and in the low energy approximation. There is a whole machinery of how one constructs states that minimize such uncertainty principle. So this is in particular Schrödinger-Robertson uncertainty rather than Heisenberg, because it's more tight. And essentially the key thing to know is that having a pair of observables for which you want to minimize uncertainty, one can construct this kind of A operator, and then states that minimize the uncertainty stated above are eigenstates of the equation, this linear combination of A and A dagger. And so that's something that one essentially can now sit down and solve. And I would like to just highlight that the result is a state that most generally is a correlated state so the M's here are essentially labeled internal states. So they are labeled by M because it's easy to remember, and then they represent different mass energies. And there are different center of mass states psi for each internal energy component. So a general such state is necessarily an entangled state with entanglement between center of mass and position. Now we will maybe just to also highlight already without giving really any technical details yet, is that for a system with trivial internal state space, so just one possible state, we have one well-defined minimum uncertainty state for the center of mass. And if you look how such states look in the low energy limit, so it's not necessarily that you look in great details in this, but in the low energy limit, we recover that such states are Gaussians, but are parameterized or depend directly on the mass energy. So this means for a particle with single mass parameter, we recover what we expect, namely a Gaussian state, but for a general system with some internal energy spectrum, we find that for each different internal state, there is essentially a different Gaussian distribution that is necessarily associated with the center of mass. So the main thing to see is that what one typically interprets as a peak momentum of a Gaussian here directly depends on M, and this is of course what we would naively guess. If I want to have a state that for different masses moves with some common group velocity, then the peak momentum of the distribution necessarily has to depend on mass. But there is another dependence on mass that is not so intuitive to guess, and this is the width of the distribution. So I will only show you here this relation between the different distributions, and then I will just directly go to conclusions because we are already reaching an hour, but this will perhaps allow to see best what's going on here. So if you consider some Gaussian, sorry, let me do like this. If you consider a Gaussian state for a system with some different internal mass energy, so we have some common, our naive first guess, so a Gaussian center of mass tensors some arbitrary internal state. After some period of free evolution, each of the mass energy components will evolve differently. So this exactly captures this fact that if we have a common momentum, but a spectrum of masses, the velocities will differ. Also, the rate of spreading of these wave packets is different. Now, if we ask how the minimum uncertainty state evolves, so this is the same mass spectrum with the same weights, but in this correlated state, after some period of free evolution, we find that the distribution, of course, expands, but all the mass energy components are essentially still localized on top of each other, allowing for the best configuration space localization of the state allowed by quantum mechanics. So now this delocalization was curiously considered to be some fundamental limitation to how such composite particles evolve. If that was true, actually, this would mean that any idealized model of a clock that essentially is a particle with the evolving internal states, and states can evolve in time only if they differ by energy. So essentially, this would mean that any idealized quantum clock would necessarily have to delocalize like this, which would mean essentially that all clocks would disintegrate after free evolution. Well, if this was true, that would really mean some fundamental limit to this idea of measuring or associating time with an idealized clock. But of course, this is not the case. So this was just an artifact of the modeling. And this state is essentially the optimal state to pick for a dynamically modeled quantum clock. If you want that it follows some trajectory in space-time that is fully compatible with quantum theory, so we don't need to assign just some fixed classical trajectory, but it evolves quantum mechanically, but nevertheless has the trajectory compatible with some semi-classical path through space-time. And as I promised, I'll finish here. There are a couple of properties of these states that are perhaps nice and fun, but I'll just jump directly to the conclusions. So I advertised composite point-like quantum particles as idealized quantum sensors, clocks, quantum test masses, or thermometers, or particle detectors. They are interesting from the perspective of a possible test of quantum mechanics and relativistic gravity, non-Newtonian gravity, because essentially internal states can allow us to uncover some relativistic effects, namely time dilation or redshift effects, even if center of mass is essentially non-relativistic. An interesting aspect of this research is a new class of states that are defined as minimizing position and velocity uncertainty principle, and that describe composite particles with semi-classical space-time trajectories. With this, I truly finish, and I'm happy to take any questions.
Thanks very much, Magdalena. That was a really interesting talk, very fascinating overview of this new emerging area of physics. I think there's one question being queued up already from Bruce Yabsley. He says, Magda, this is an excellent talk, re the XV MUS discussion. You said this means that a quantum clock need not become delocalized, but how easy would it be to prepare a system in an XV MUS state?
This is actually an excellent question. I don't know the author. I don't know if Bruce, maybe you are experimental physicist, so that's maybe the reason for the curiosity. Interestingly, everything here somehow falls together. So if we think of how we prepare Gaussian states, well, we can take a particle, put it in a harmonic trap and cool it to the ground state. Now, if we ask what is the ground state of a particle with the spectrum of internal energies that is cooled to the ground state of a harmonic trap, and what we find essentially is for a trap with a fixed frequency is this kind of MUS state. So this could be seen as a recipe to prepare such states. So one can obtain them by cooling composite particles in harmonic traps. Hope that answers, or at least to some extent, highlights the direction for preparing such states.
I think that's very good. So there was a question motivated by Simon's question in the Simon Haynes question. He just wanted to know. Yeah, if you could just say a little bit more, please, about the assumption in the first Hamiltonian that you wrote up, which involves just the G00 term of the tensor. Could you just say a little bit more about the assumptions that enabled you to write that simplification?
Right. Yeah, I'm seeing the chat as well. So the fact that there is just G00 visible, that per se is not the point-like. So the point-like fact is that at all I can use a metric that is at a single point. So this point-like here is really about the physical actual extent of the system. So if I have an extended system, I cannot say that it's placed in a position where the gravitational field has a value G0 of X or any other. Now, there are other metric components that are hidden in the momentum. You can see now in the slide that is up that I have both contra and covariant indices on P. If you write everything in terms of contravariant momentum, P with the index up, there will be other metric components and they are relevant there. So if you want to, for example, find the Hamiltonian, and you can find it in the references below and also in many papers by other people. If you want to find the Hamiltonian in the low energies for a particle that is on a static symmetric metric, you'll find that there will be additional terms that come from this PI, the kinetic term. So there are other metric components. The fact that it's G0 not only here is because I've used the trick with the position of the index to avoid too many symbols. The point-like aspect is here present because I can just write G0 and Gij at some particular value X. So essentially, in this sense, I use a metric parameterized with some fields, and I can put a quantum system that couples locally at one point to that field. If I have an extended system that's no longer possible, and I have to either write it explicitly in terms of how it's composed or model in some way some tidal effects.
All right. One of the nice one of the interesting results of this is the fact that, as you pointed out in your final slide, you can get invariance with respect to Lorentz transformations, despite the fact that you're starting with a relatively simple modification, effectively, of the Schrodinger equation. So could you just say a bit more? Why is that possible? In other words, we're implying that all of special relativity, in a sense, has been captured by this model. All up to 1 over c square. I've put up, actually, I think you see probably the Q&A covering the screen. And for
For some reason, I cannot hide it now. Sorry, maybe I'll do like, oh, I see. All right. These states are Lorentz covariant up to 1 over c square, obviously, because the Lorentz factor is captured by these dynamics up to 1 over c square, as I showed you in the dynamics.
Right.
Now if one takes the Hamiltonian with the full square root, so this is the Hamiltonian that you can use for a Schrodinger equation for a first quantized particle, but with relativistic dispersion relations. Of course, it has limits to its validity, but there is a well-defined regime where it can be meaningfully used. And if you look at minimum uncertainty states for a system that evolves under this full Hamiltonian, so that's actually follow-up work by Evangel, you'll find that they are Lorentz covariant to all orders. Now the trick, like how did we manage to get it while we seemingly went all the way to Newtonian limit and then just included mass energy equivalence? That's essentially because the time dilation of the redshift effect and mass energy equivalence are what I like to say are two different sides of the same coin. So the dynamical underpinning of the kinematic Lorentz, let's say, if we look at Lorentz factors as something that transforms some reference frames, so just mathematical as transformations between some coordinates. The reason that this is or how it's related with the symmetry of some dynamical equation is that dynamics of particles or of systems features this mass energy equivalence. So essentially, there would now be redshift described by Lorentz factor if all internal energies were not coupling to the mass. If you look on the kinetic term, for example, if the inertial mass that appears in p squared over 2m, if it didn't contain inside, so to say, all the internal energies, if you start the expansion, we wouldn't recover this Lorentz factor. So this is how the Lorentz invariance between reference frames is dynamically implemented, so to say. I hope that that clarifies. And that's why this mass energy equivalence is so powerful, because you can capture the redshift effects to lowest order in c square by understanding what's the non-relativistic description of the system and bootstrapping the mass energy equivalence. Of course, this is limited to just 1 over c squared, so you cannot bootstrap to this whole square root relativistic dispersion relation, but that's how one can get this Lorentz covariance to lowest order, even though starting from systems that are in a sense very close to being non-relativistic.
Would you think there'd be any reason to think about? I mean, what you set up here is a lovely essential theory, if you like, simplified theory, which is extremely useful and certainly is, provides a lot of insight into some of these things. Is there any motivation or any necessity, do you think, to go beyond the Schrodinger equation, start talking about the Dirac equation or Proctor equation or something like that?
Yes, certainly.
Relativistic
equations. So clearly there would be effects where we might be interested in some composite particles that might actually exhibit the genuine field theory effect. So I mentioned neutrinos. Actually, they are, as far as we know, they are probably very light. They have spectrum of masses, so they are a nice candidate to apply this kind of theory. But then also there will be a good motivation to consider them in terms of a full field theory. So essentially starting from where we directly where we started our effective theory. Another context where one would like to extend this or incorporate this into Dirac equation, as has been mentioned, is when we start to think of internal energy that is, for example, associated with the spin. So different spin projections on magnetic field would have different energies, and we can consider spin precession as a clock. Now, to lowest order, curiously, if you start to do this for an electron, at least in some typical laboratory setting of a penning trap, you find that to lowest order, you can actually get away in a sense that the relevant quantities are correctly described by considering that the spin projections contribute to the mass energy. But this obviously fundamentally is not correct, because spin is not a scalar like the mass energy is. So spin has additional transformation properties, and it's not, of course, a spin energy will contribute to the mass, but there will be additional effects associated with the spin just by the fact that this is a spin degree of freedom and not the mass. And so if I want to fully capture related effects for when internal energy is associated with the spin, this is a very good motivation to start with the Dirac equation I believe static symmetric metric should be still fine. There are wonderful works from groups working with geonium, trapped electrons used for high precision experiments that we actually used in our works with the electron implementation of a clock to look at this, but there is a lot of ground to cover to look at some complete say description of a particle with the in this kind of limit with quantized mass energy and the spin together. So there can be separate contributions essentially that can be explored in parallel.
Oh, that's really, really interesting. I don't see any more questions. So I think with everyone's permission, we might think about wrapping up. If you're happy, Magda, is there anything else you prefer to say? And thank you very much for agreeing to give the talk, agreeing to the invitation. It was a great start to 2022. I remind everyone that our next talk, I believe, is being given by Howard Weissman, which will be terrific, on March the 24th. We'll update people with emails when the titles and things like that are finalized. In the meantime, thank you everyone for joining, and we hope to see you again next time. Thanks, Magda.
Thanks, everyone.